3 minutes ago, the Hubble Space Telescope pivoted in orbit and locked onto something trailing Voyager 2, something faint, something moving, something scientists at NASA say shouldn't be visible from this distance at all. And what they are finding out there, nearly 13 billion miles from Earth, isn't what most people think. It's stranger, it's real, and it's happening right now. For 48 years, Voyager 2 has been running. Launched August 20th, 1977, from Cape Canaveral's Launch Complex 41, she is the second farthest human object in existence. Only her twin sister, Voyager 1, has traveled deeper into the dark. But here is the mystery that pulled Hubble's gaze. In recent months, mission engineers at NASA's Jet Propulsion Laboratory in Pasadena noticed something in Voyager 2's telemetry that didn't fit the models, a subtle irregularity, a whisper in the data, a signature no one had prepared for. And so, for the first time in decades, one of humanity's most powerful telescopes was asked to look at what appeared to be empty space and see what might be trailing behind her. Now, before your mind races to aliens, to conspiracies, to something NASA is hiding from the public, stop, because it is none of those things. What is actually happening out there is stranger than science fiction, more important than any rumor, and completely, publicly verified by the world's most respected space agencies, including NASA, the European Space Agency, and the Space Telescope Science Institute in Baltimore. Stay with me, because what you learn in the next 15 minutes will change how you see our place in the universe. And it will change how you understand the fragile, dying machine that carried us to the very edge of it. To understand what Hubble is seeing, you first have to understand what Voyager 2 actually is. She weighs 1,592 pounds. She carries 11 scientific instruments. She stands roughly the height of a small car. And she runs on plutonium-238, a radioactive isotope decaying slowly and silently inside 3 radioisotope thermoelectric generators bolted to her frame. When she launched, Jimmy Carter was president. Star Wars was still in theaters. The Bee Gees were #1 on the Billboard charts. And the engineers who built her, men and women at JPL in Pasadena, California, quietly assumed her mission would end after Saturn. It didn't. Voyager 2 kept going. She flew past Jupiter in July of 1979, past Saturn in August of 1981, past Uranus in January of 1986, the only spacecraft in human history to visit that ice giant. Then Neptune in August of 1989, and then she kept going. On November 5, 2018, at approximately 119 astronomical units from the Sun, Voyager 2 crossed the heliopause, the invisible boundary where the Sun's magnetic influence ends and the true interstellar medium begins. She became only the second human-made object ever to physically enter interstellar space. Think about what that means. Every satellite, every probe, every telescope humanity has ever built, all of them, except Voyager 1 and Voyager 2, are still inside the bubble our sun blows around itself. Only these two have crossed the border. Now here is where the story turns urgent. Voyager 2's plutonium power source loses about 4 watts of output every single year. By 2026, this year, mission scientists at JPL have confirmed she has already been forced to shut down 4 of her 5 remaining scientific instruments to conserve energy for the essentials. The mission that has taught humanity more about the outer solar system than any other endeavor in history is dying. And that is exactly why Hubble was pointed her way. So here is what Hubble is actually seeing. Not a ship, not a signal, not a message from something intelligent following our probe. Hubble is watching hydrogen. Specifically, a faint ultraviolet glow called Lyman alpha emission light produced when hydrogen atoms, drifting in the vast emptiness between stars, are struck by radiation and re-emit that energy at a very specific wavelength. It is invisible to the human eye. It is faint beyond imagination. And along the path Voyager 2 is carving through interstellar space, that glow is behaving in ways scientists did not predict. You may not realize this, but for decades, researchers assumed the space beyond the heliopause was relatively uniform. A thin, quiet soup of particles. Cold, empty, featureless. It isn't. Data from Voyager 2's plasma science experiment, before it was shut down to preserve power, combined with Hubble's ultraviolet observations, has revealed something remarkable. The interstellar medium is denser, more structured, and more turbulent than any pre-2018 model predicted. There are clumps out there, filaments of hydrogen, regions where the density of interstellar gas jumps by factors nobody expected to see. But what does this actually mean for you? It means the empty space between stars isn't empty at all. It has weather, it has texture, it has structure, it has neighborhoods. And Voyager 2 is the only object we have ever built that is physically inside it, sending back real, direct measurements. Now, two new questions crack wide open. First, what is causing those density spikes Hubble is tracking behind her? And second, more urgently, how much longer does Voyager 2 have to keep measuring them before her power runs out completely, and this window closes forever? To understand what Hubble is really watching, you need to picture something almost impossible for the human mind to hold. Voyager 2 is now more than 12.8 billion miles from Earth. Her radio signal, traveling at the speed of light, the absolute speed limit of the universe, takes over 19 hours to reach the Deep Space Network antennas in Canberra, Australia. Canberra is the only station on the planet that can still hear her voice, 19 hours. One way. When engineers send her a command, they wait more than a day and a half to know if she received it. If something goes wrong, they cannot fix it in real time. They cannot even watch it happen in real time. And yet, she is still transmitting, still measuring, still whispering back to us across the void. Now, here is what scientists didn't expect. When Voyager 2 crossed the heliopause in 2018, her instruments recorded a sudden, sharp jump in the density of charged particles, a compression in the interstellar plasma that shouldn't have been that abrupt. The instrument wasn't designed to find that, and yet it did. Hubble's observations are now confirming why. Some researchers at the University of Iowa, where much of Voyager's plasma data has been analyzed for decades, believe the sun's heliosphere is actively compressing the interstellar medium ahead of it, like the bow wave of a ship pushing through calm water. Others at Johns Hopkins suggest we may currently be passing through a region called the local interstellar cloud, a wisp of slightly denser gas our solar system drifted into tens of thousands of years ago and will drift out of tens of thousands of years from now. Data suggests both may be true at once. But here's where it gets strange. The direction Voyager 2 is heading toward the southern constellation, Pavo. The Peacock is different from Voyager 1's trajectory, which is heading toward Ophiuchus. And the interstellar environment on Voyager 2's side of the sky is measurably different. The magnetic field is oriented differently. The particle density is different. The turbulence is different, which means the space between stars isn't the same in every direction. Think about that for a moment. For all of human history, from the first stargazers on the plains of Mesopotamia to Galileo to the astronomers of today, we have looked up at the night sky and assumed it was one thing, one vast uniform darkness stretching in every direction. Hubble and Voyager 2, working together, are proving it isn't. Space has geography. Space has regions. Space has neighborhoods. And here's what almost nobody talks about. Every observation Voyager 2 makes right now is the last of its kind humanity may see for generations to come. There is no replacement mission funded. There is no Voyager 3 sitting in a hangar. There is no probe on any drawing board that will reach interstellar space in your lifetime or in mine. When Voyager 2's plutonium falls below the threshold to power even a single instrument, projected by JPL, sometime between 2027 and 2030, the data ends, not delayed, not paused, not rerouted, ends. And here is a question that keeps mission scientists at JPL awake at night. What happens if the single most important discovery Voyager 2 is capable of making hasn't happened yet? What if the observation that rewrites physics is still waiting 3 years from now, 5 years from now, and her batteries died 2 months before she reaches it? That is not a hypothetical fear. That is the reality her engineers are racing against right now, which is why Hubble was pointed her way. Because if Voyager 2 herself cannot keep measuring, then Hubble, from Earth orbit, might just be able to see her wake from here. And what Hubble sees next is where everything changes. This is where it affects you. Because what Hubble locked onto isn't a ship following Voyager, it isn't debris. It isn't an anomaly, it isn't hidden, it isn't classified. It is the wake she is leaving. As Voyager 2 pushes through the interstellar medium at 34,390 miles per hour, she is disturbing the hydrogen atoms around her very, very slightly. And Hubble, with its Space Telescope imaging spectrograph, is sensitive enough to detect the faint ultraviolet fingerprint of that disturbance from Earth orbit. For the first time in the history of our species, we are watching a human-made object physically interact with the material between stars, not in a laboratory, not in a computer simulation, not in a theory paper, there, real, right now. This isn't a signal we weren't supposed to receive. It's a signal we never dreamed we would be positioned to receive, because until Voyager 2 crossed that heliopause boundary in 2018, no one on Earth knew such a measurement was even physically possible, and it is rewriting the textbooks in real time. Researchers at the Space Telescope Science Institute in Baltimore, working alongside the Voyager team at JPL, are now using this combined Hubble-Voyager dataset to build the first true map of our local interstellar environment, not guessed, not modeled, not extrapolated, measured. You are alive during the exact narrow window in which this is possible. Before Voyager 2 crossed the heliopause impossible, after her power dies impossible again for decades, possibly a century, possibly longer. Right now, the only window humanity has ever had, or will have in our lifetimes, to see the space between stars from the inside. That is what Hubble is looking at. Not a mystery, not a threat, not something hidden from the public. A goodbye letter, written in ultraviolet light, traced across the gulf between stars by the farthest emissary our civilization has ever sent, and every day the mission continues. We learn one more sentence of it, but there is one more thing. Because bolted to the side of Voyager 2, riding along with her into the interstellar dark, is something even more remarkable than her instruments. Next week, I'm going deep on the golden record, the 12-inch gold-plated copper disc engineers attached to both Voyagers in 1977, the images, the sounds, the greetings in 55 languages we chose to represent all of humanity to whatever might find her a billion years from now. And I'm going to reveal the one recording NASA scientists still quietly argue about including 48 years later. Subscribe now, because that story reveals something about who we were in 1977 that most people alive today have never heard. And before you go, I want to hear from you. If you could send one sound, one single sound from planet Earth to whatever intelligence might find Voyager 2 a million years from now, what would you choose? A child's laugh, a thunderstorm, a song, a word? Leave your answer in the comments below. I read every single one. Because out there, nearly 13 billion miles away in the dark between stars, she is still going. And so, are we